All right, friction and gravity. Would you like to be an astronaut and work on the International Space Station? If so, you'll train at NASA's Neutral Buoyancy Laboratory. This lab has the world's largest indoor pool containing more than 234 million liters of water. The pool is used to simulate the feeling of weightlessness experienced by astronauts in orbit. In the depths of the tank, you'll wear a pressurized spacesuit as you train on full-size models of the objects that you'll service outside the space station. You'll spend about 10 hours underwater for every hour you'll work in space. So think about this. How would working to repair wires in the Hubble Space Telescope be harder to do in space than on Earth? All right, what factors affect friction? If you slide a book across a table, the surface of the book rubs against the surface of the table. The force that two surfaces exert on each other when they rub against each other is called friction. Two factors that affect the force of friction are the types of surfaces involved and how hard the surfaces are pushed together. The football player in Figure 1 is pushing on a blocking sled. If his coach wanted to make it harder to move the sled, the coach could change the surface of the sled. Covering the bottom of the sled with rubber would increase friction and make the sled harder to move. In general, smooth surfaces produce less friction than rough surfaces. What would happen if the football player switched to a much heavier sled? He would find the heavier sled harder to push because it pushes down harder against the ground. Similarly, if you rubbed your hands together forcefully, there would be more friction than if you rubbed your hands together lightly. Friction increases when surfaces push harder against each other. Friction acts in a direction opposite to the direction of the object's motion. Without friction, a moving object will not stop until it strikes another object. All right, so the strength of friction depends on the types of surfaces involved. I want you to rank the surfaces above by how hard it would be to push a sled over them. 1 being the easiest, 3 being the hardest. Each of these surfaces are flat. What does this ranking tell you about the amount of friction over these surfaces? All right, there are 4 types of friction. The first type we're going to talk about is sliding friction. Sliding friction occurs when two solid surfaces slide over each other. Sliding friction is what makes moving objects slow down and stop. Without sliding friction, a penguin that slid down a hill wouldn't stop until he hit a wall. So you're going to label 5 examples of sliding friction and compare with a classmate. Along these pages, you're going to find your 5 examples of sliding friction and label them. All right, the next type is static friction. Static friction acts between objects that aren't moving. Think about trying to push a couch across the room. If you don't push hard enough, it won't move. The force that's keeping you from moving it is static friction. Once you push hard enough to overcome static friction, the couch starts moving and there's no more static friction. However, there is sliding friction. So you're going to label 5 examples of static friction on the same pages. All right, then we get to fluid friction. Fluids, such as water and air, are materials that flow easily. Fluid friction occurs when a solid object moves through a fluid. Fluid friction is easier to overcome than sliding friction. This is why sidewalks become slippery when they get wet. So label 5 examples of fluid friction on those pages. Also, you're going to draw an arrow representing the frictional force at work. All right, rolling friction is the last one. When an object rolls across a surface, rolling friction occurs. Rolling friction is much easier to overcome than sliding friction for similar materials. That's why it's easy to push a bike along the sidewalk when the wheels can turn, but much harder to push the bike if you're applying the brakes and the tires slide, not roll. So you're going to label 5 examples of rolling friction on these pages as well. Then draw an arrow representing the frictional force at work. All right, so apply it. Your family is moving and isn't sure how to best overcome friction while moving furniture. You have a spring scale, wood blocks to represent your furniture, and sandpaper, aluminum foil, marbles, and olive oil as possible surfaces to slide your furniture over. Design an experiment that will help you determine which material will reduce friction the most. You know that friction occurs between surfaces when they slide against each other. If you measure the applied force required to push something across a surface, you know that your applied force would increase or decrease as friction increased. So, how would you determine your applied force in this experiment? What variables would you have to control to keep your results accurate? Draw the data table you would use when performing this experiment. All right, and assess your understanding. Name 4 types of friction and give an example of each. What types of friction occur between your bike tires and the ground when you ride over cement, ride through a puddle, and apply your brakes? All right, moving on to what factors affect gravity. A skydiver would be surprised if she jumped out of a plane and did not fall. We are so used to objects falling that we may not have thought about why they fall. One person who thought about it was Sir Isaac Newton. He concluded that a force acts to pull objects straight down towards the center of Earth. Gravity is a force that pulls objects toward each other. Universal gravitation. Newton realized that gravity acts everywhere in the universe, not just on Earth. It is the force that makes the skydivers in Figure 2 fall to the ground. It is the force that keeps the moon orbiting around the Earth. It is the force that keeps all the planets in our solar system orbiting around the sun. What Newton realized is now called the law of universal gravitation. The law of universal gravitation states that the force of gravity acts between all objects in the universe that have mass. This means that any 2 objects in the universe that have mass attract each other. You are attracted not only to Earth, but also to the moon, the other planets in the solar system, and all of the objects around you. Earth and the objects around you are attracted to you as well. However, you do not notice the attraction among small objects because these forces are extremely small compared to the force of Earth's attraction. All right, so observing gravity. Newton published his work on gravity in 1687. What observations might you make today that would lead you to the same conclusions about gravity? Write down your ideas below. All right, factors affecting gravity. Right here, you're going to underline the factors that determine how strong the gravitational force is between 2 objects. All right, factors affecting gravity. A gravitational force exists between any 2 objects in the universe. However, you don't see your pencil fly towards the wall the way you see it fall towards Earth. That's because the gravitational force between some objects is stronger than the force between others. You observe only the effects of the strongest gravitational forces. 2 factors affect the gravitational attraction between objects. That's mass and distance. Mass is a measure of the amount of matter in an object. The standard unit of mass is the kilogram. The more mass an object has, the greater the gravitational force between it and other objects. Earth's gravitational force on nearby objects is strong because the mass of Earth is so large. The more massive planets in Figure 3 interact with a greater gravitational force than the less massive planets. Gravitational force also depends on the distance between the object's centers. As distance increases, gravitational force decreases. That's why Earth can exert a visible gravitational force on a pencil in your room and not on a pencil on the moon. So, gravitational attraction depends on 2 factors, mass and distance. Suppose there was a solar system that looked like this. Use the diagram below to compare the gravitational force between different planets and their sun. Assume all planets are made of the same material, so bigger planets have more mass. Okay? You're going to circle the object in the outermost orbit that experiences the greatest gravitational pull from the sun. Then planet B's force arrow from the sun's gravitational pull should be longer or shorter than the arrow from planet A. Draw what planet C would look like if it were the same distance from the sun but experienced a smaller gravitational pull from the sun. All right, weight and mass. Mass is sometimes confused with weight. Mass is a measure of the amount of matter in an object. Weight is a measure of the force of gravity on an object. When you stand on a bathroom scale, it displays the gravitational force Earth is exerting on you. At any given time, your mass is the same on Earth as it would be on any other planet, but weight varies with the strength of the gravitational force. The dog in Figure 4 has a different weight at different places in the solar system. On the moon, he would weigh about 1/6 of what he does on Earth. On Mars, he would weigh just over 1/3 of what he does on Earth. All right, so the Mars Phoenix lander weighs about 3,400 newtons on Earth. It weighs about 1,300 newtons on Mars. The first scale shows the dog's weight on Earth. Predict its weight on the moon and on Mars. Enter those weights in the boxes on the other two scales. All right, what happens to the gravitational force between two objects when their masses are increased? What happens when the distance between the objects increase? All right, if the mass of Earth increased, what would happen to your weight? What about your mass?